Okay, so today we're going to talk about colligative properties. We've already started this when we were talking about Raoult's law. I like to include it with the gas laws mainly because of the pressures. I was going to include colligative properties with that, but then I was like, it actually belongs with solutions. So that's why I didn't include it on your test or your quiz, but it will be on this unit test and quiz. Anyways, so today we're not going to do a review on Raoult's law. There's already a video on that, but you are going to be solving practice problems on it this week. But real quick, before I jump into today's lesson, we're going to talk about basics of solutions, electrolytes, all that stuff, just so you get, reacquainted with the terms. So let's talk about some things that we need to know before we go on to today's topic. So first, let's do solutions. So a solution is made out of two things. You have your solvent and solute. So your solvent does the dissolving. Your solute, that's a horrible arrow. Your solute gets dissolved. Okay. So, what happened? Anyways, so we have these two terms. You need to be familiar with them. We've been going over this since Unit 1. And then the other thing we have to be familiar with is the Advance Hof Factor. And this is represented by an I, drawn like this. It's not just my little penmanship or whatever. That's literally how it's drawn. So the I represents how many ions you have in solution. So I'm going to give you some examples. We have electrolytes, and this is all a review because I've already gone over this, and non-electrolytes. Okay, so your electrolytes are going to be your ionic compounds. And then non-electrolytes are going to be covalent compounds. Like sugars and alcohols and stuff like that. Ionic compounds, remember, is a metal, non-metal. So I'm going to give you an example of each one. We're going to do methanol for this one, which would be CH3OH. And then the Advance Hof Factor for any covalent compound will be 1. And then for an ionic compound, it's based on how the ion splits up. So say we had magnesium chloride. I'm going to give you 2. We have magnesium chloride, and then the other one we'll have is aluminum sulfate. So first, let's figure out, based on the charges, how many, I already gave you this one, but for this one, just as a little review, how many charges, how many of each part do we have? So we drag the charges, and then that means we have 3 and 2 because of the charges. So I'm going to rewrite this so you don't see that. So you have Al2SO43. So when we have our little ionic equation, what happens is, and if you're wondering where I'm getting these numbers from, I really suggest you go and review your periodic table notes because we went over this at length. You need to be able to just split these up by looking at them. Or if you need to look at the table, you need to know where to look. It's all based on the groups. So we have, and then 3, SO4, -2. So As you can see, these are both different. They're both going to have different Advance Hof factors. So for magnesium chloride, you have to count up how many ions you have. So we have 1 here and 2 there. So that means I is equal to 3. And then over here we have a 2 and a 3. You can usually do this by just using this, but say you had this. That means you have I equals 5. So that would be how you're able to determine how many ions you have in solution. It's like how many moles of ions you have. Alright, so now that we've gone over the basics, we're going to jump into today's topic, which is, I'm going to go to a new page, I think. No, I got room. Osmotic pressure. So osmotic pressure is dealing with how solutes and solvents interact with a semi-permeable membrane. So kind of like a cell membrane, where you heard about osmosis and the transmission of different molecules that can go through the membrane, and then you also have transporter proteins and all that other stuff. Osmotic pressure talks about when you have a semi-permeable membrane and the solvent's able to, use equilibrium to space itself out and achieve that balance, how much pressure do you need to kind of force it back through that membrane? So I'm going to write down the definitions so we have those. So we have the flow of a solvent between solutions. Separated by a semi-permeable membrane. Okay, so osmotic pressure is the minimum amount of pressure required to stop osmosis from happening. And there's actually a formula that's derived from the ideal gas law that we're able to use to calculate this. Let me get a drink real quick. Okay, so if you need to copy these definitions, pause the video and copy it. I'm going to move on. Okay, so the formula for osmotic pressure. Well, actually, let me draw you a picture first. That might help. So let's use a YouTube, not the website, but I'm going to just copy this so I don't have to draw it again. Okay. So we're going to have our semi-permeable membrane. On the left, we're going to have our solvent, so that'll just be like pure water or whatever. All right, there you go. There's your water. And then on the right, we're going to have our solution for our problem. So maybe I drew that a little too high. I drew both of them way too high. We'll just do it here. And then this one come down a little bit. They got to be even when we start, but I didn't want them too high to show this. So what's going to happen is, let me pink to kind of show because it's bright. You have H2O, and then we have some solute solution. Or we have a water solution. We'll just put that. And then this has 0.01 gram of solute mixed into it. And then there's your H2O. So what's happening is the water is undergoing equilibrium, going through this semi-permeable membrane. Like, the water can go through it both ways, but the actual solute that's dissolved in it cannot go through it. So it's trapped on this other side. That's kind of what your cells do to kind of regulate themselves. Not kind of, it's how they regulate the pressure inside of them. I mean, without this, we wouldn't exist. So a lot of stuff wouldn't exist. Alright, so here, what happens is when you have osmosis, the left side's gonna, go down a little bit. And it's gonna push this side up higher. All the while, you do have pressure pushing down on it from outside the container, and you still have your semi-permeable membrane. But when you have enough pressure of it, enough pressure exerting itself from the outside, you can force all this stuff. Where'd my cursor go? Anyways. You can force all this water back through. The solute's still going to be on the right side, but you can at least force the water back in. And here we go. So the way to calculate it is derived from the ideal gas law. So you have PV equals nRT. Now, the formula for, I'm going to label this, although you guys should know this by now. So the formula for osmotic pressure is you could have P, which PV equals nRT. You would divide the volume out, right? So I'm showing you how it's derived. This isn't the actual formula. So then you have P equals nRT over V. And we just learned about dilutions. So if you remember, molarity equals N over V, right? So if you look here, I'm going to use yellow, N over V. So the formula for osmotic pressure has to do with the amount of ions in solution with the Advance Hof Factor, but it's essentially this. So you have pi, let me label this. So you have pi, or it's like capital pi, it's written like this. All right, bad drawing. Equals I times molarity times the gas constant times the temperature. And you're going to end up usually finding the answer in atmospheres because it's derived from that formula. So I'm going to go over an example real quick, and then that should pretty much do it for this, because this is very, very straightforward. Let's see. No, we could do two. We'll do two examples. That should be plenty. So I'm going to draw the YouTube again. And this one's already gone through its equilibrium where the solvent has pushed through. So we're going to have that, and then the water on the right side is going to be just a little bit higher. And then here's this. Okay, so we're going to have an outside force. We need to figure out what pressure is needed at the minimum pressure to force that water back through the membrane. So let's say that on the right side, we had 0.01 grams of solute. We don't know what it is exactly, but we can still figure it out. So the osmotic pressure, we're going to find out Well, I'm going to give you the pressure for this one. We're going to find out what the molar mass of this solute is because we don't know what it is. If you knew what the molar mass was, you could figure out the pressure. But since we don't know it, we're going to solve the molar mass, which is something that's done a lot with medicine. So we have 10 to the negative 3 atmospheres. So this is the osmotic pressure. So we need to figure out what the molar mass of this is. So simply, we're going to do some algebra. Equals. So we're just going to assume I equals 1. Because it's not ionic, we're going to assume it's 1. So 1.47 times 10 to the negative 3 atmospheres equals 1 times, we don't know what the molarity is. That's what we're going to be figuring out. And then we're going to assume that this whole solution is the volume for the whole thing is 1 liter. Just so, like, we don't know what it actually is, but for right now we're going to assume it's 1 liter so we can figure out the molarity. Actually, no, I gave you that. My bad. We're not assuming anything. This whole thing is 1 liter. Ignore everything I just said. So we have I times M times 0.0821 liters times atmospheres over moles times Kelvin times the temperature. And the temperature is 25 degrees Celsius, which would be 298 kelvins. So now we have to isolate the M. So say we have pi equals I, not lowercase m, RT. We just divide out I RT on both sides. And then we're going to be left with M. So let's do that over here. We're going to divide this out. I'll write all the units just so we have them. I don't want to be instilling bad habits yet. Okay. So that cancels and that cancels. And then we're going to divide it over here. And then you're going to see that we're going to end up with moles over liters. So we have 1 times 0.0821 liters times atmospheres over moles times kelvins times 298 kelvins. So just from the bottom, we know we can cancel the kelvins out. As the atmospheres is on top, when we are doing the division, top and the bottom are going to flip. So this is going to end up on the bottom of this. It'll cancel. And then the moles is going to end up on top. So let's plug this in the calculator and figure out what the answer will be for the molarity, which we can then use to find the molar mass. So we have 1.47 EE negative 3 divided by parentheses. Do parentheses for the bottom just because otherwise you're going to get an error. Not an error, but you're not going to get the right answer because it's going to read it out differently. So our answer is going to be about 6.01. So M equals 6.01 times 10 to the negative 5. And then that's moles, liters, negative 1. So I'm going to continue on to the next page. So if you need to copy this, pause it real quick. And then we're going to keep moving. So remember we had a mass of the solute at 0.01 grams. And then our molarity was equal to 6.01 negative 5. And then that's moles over liters. So we know that we had 1 liter. So it doesn't matter. We know because it's moles over 1 liter, this is how many moles we have. We don't have to do any further division. So now, if you remember, molar mass grams over mole. So that's the last step that we have to do. So that means we have 0.01 grams divided by 6.01 times 10 to the negative 5 moles. And then that's going to give us our answer. So divided by answer. And then we're at about 166.43 grams over moles. And that would be your answer for this particular problem. So now say we wanted to calculate the pressure. I'm going to just make something up real quick. So here we go. And I'm going to make it up as we're going, so hopefully this works. So I'll be a little higher and make this a little bit lower. There you go. And then over here. Okay, so we're gonna say that we had, what can we dissolve in there? We'll just say that we're dissolving KCl, into there, and it was, I don't know, like 0.37 molarity. Which is, let's do something more realistic, 0.5 molarity. And then we're going to have a volume of 350 milliliters. And then we're going to have to figure out what the osmotic pressure is for a solution that has 350 milliliters mixed with 0.5 molar KCl. And then obviously the solvent is going to be H2O, and it was flowing this way. So let's set up our equation. We have big pi equals I times molarity times the gas constant times temperature. Let's say the temperature is, I don't know, like 32 degrees Celsius. We're going to make it a little warm. So first things first, let's convert this to liters. So volume is 350 milliliters. Take a second to try and figure out how you would convert that to liters. So what you would do is you have to divide this by 1,000. So you do 1 liter over 1,000 milliliters, and that cancels. So you're going to be left with 0.35 liters, because that's going to 1, 2, 3 move over. So we have this many liters, and we have this many moles per liter. So let's divide it. We have 0.5 moles divided by this many liters. So 0.5 mole divided by 0.35 liter, and that'll give us our new concentration. So 0.5 divided by 0.35. So you have 1.43 molar KCl. And then now the last thing we have to do before we start plugging things in is we have two things. Temperature, we've been doing this for a while. So you have 32 degrees Celsius plus 273. And that comes out to 305. 305 kelvins. So last thing we have to do is figure out the Advance Hof Factor. So KCl splits to K plus 1 plus Cl negative 1. So that means you have 2 ions. So your I is going to be 2. So let's plug everything in and figure out what our answer is going to be. That's a big pi symbol. All right. So pi equals 2 times molarity is 1.43 m times 0.0821, and that's liters times atmospheres over moles times Kelvin. So right now we can already cancel, because it's moles over liters, so that cancels. And then we have our temperature, which would be 305 kelvins. So that's going to cancel. And if you don't understand why that cancels, it's moles per liters, and then you're multiplying that by liters over moles. So that's why those two cancel right there. So now all that's left to do is plug this into the calculator and figure out the answer. So we have 2 times 1.43, and you don't need parentheses because it's just straight multiplication. Just don't screw up on the decimals or anything. Times 305. So our osmotic pressure is going to be kind of high. It's going to be 71.6 atmospheres. 71, so pi equals 71.6. We'll do 62 atmospheres. And that's how you would calculate the pressure. Obviously, you could calculate anything from this, but really I'm going to be the only thing I'm not going to ask you is this, because that's not really a calculation. That's just taking that. So I'm probably going to be asking you to calculate molarity. I'll be asking you to calculate molar mass, pressure, and possibly the temperature. Alright, so that about does it for this topic. We have one more thing to go over in colligative properties, and then we'll be done with this part of the unit. We're going to do some practice. You're going to have a quiz on this probably the following week, and then we're going to start acids and bases, and then we are going to be done. So, yeah, that's pretty much it.